All right, here we're talking about inverse functions, and when we're talking about inverse functions, an inverse function is really just a relation where we switch the x and the y values, where we change those ordered pairs around. So if the relation has ordered pairs a, b, then the inverse has ordered pairs b, a. All right, so what we're doing is essentially taking x and y and they're trading places. All right, so every ordered pair that's involved with that relation gets a flip-flop of the x and the y values. All right. When we talk about the inverse, we denote it this way. If I have a function f of x, the inverse is denoted as f to the negative 1 of x. And keep in mind, this is just a notation. This little negative 1 that's here doesn't do anything. I'm not going to rewrite that as x over f to the negative 1 or f to the positive 1 and say, okay, that's got a negative exponent. So I'm going to rewrite that. This would be totally incorrect. So please don't do that. That negative 1 mathematically does absolutely nothing. It's just there as a notation to denote that we want to find the inverse. So when we see something that looks like this guy, we're talking about the function, and then this guy is its inverse. All right, this is f of x. This is the inverse of f of x when we read these things. Okay, so keep in mind that is just a notation. When you see that, that should tell you that you need to find the inverse. All right. For example, if I look at something like this guy, here I want to find the inverse of this function. So I've got f of x, that's my original function, and I'm going to find the inverse. That's what this guy right here is telling me. So I'm going to take that thing and find the inverse. So I scooted that off to the side a little bit. So if f of x had the ordered pair 2, 3, the inverse is going to have the ordered pair 3, 2. I just switched the x and the y. The next ordered pair that the function had was negative 1, 4, so I'm going to have 4, negative 1. My next ordered pair for the inverse is going to be 3, 0. And my last ordered pair is going to be 5, negative 4. All right, so just take each of those ordered pairs, and I switch the x and the y. That's my inverse. All right, and now a couple questions about this. When I look at the original function, when I look at f of x, I want to know, is this a function? So again, you look at the x values. Remember, to be a function, every x value you have to have exactly one y value. Since there's no x values that are repeated, every x value has its a unique y value, so the answer is yes, that one is a function. And then it asks me about the inverse. Is the inverse a function? So again, I look at the x values, see if there's any repeated x values, and right here, I see that this 3 is repeated, and I'm with two different y values, so that one is not a function. All right? So because there's two different y values here, this one is not a function, so the answer is no. All right? So the original was a function, the inverse was not a function, and that leads us to this definition, a one-to-one function. A one-to-one function is essentially a relation where the relation and its inverse are both functions. All right. So if the original is a function and the inverse is a function, then I'm dealing with a one-to-one function. And this is kind of like a natural progression. A relation is a set of ordered pairs, and then a step up from that is a function, which is a relation where every x has exactly one y. And then a step up from that is a one-to-one function where I have a function whose inverse is also a function. All right. Another way to think of that, if you don't want to find the inverse, we can also think of one-to-one as being this. And essentially this is saying the same thing. Oh, sorry about that. Essentially this is saying the same thing. What it's saying is every x has exactly one y. That's the definition of something being a function. And then every y having exactly one x, that's essentially the inverse being a function, because when we switch them, those y's become our x values, all right? So when I look at the example above, if I wanted to determine if this guy was a one-to-one function, the answer here would be no for two reasons. This is not one-to-one. And there's two possible explanations as to why this is not one-to-one. The first definition that we have for one-to-one, we just look at the function and its inverse. Well, here, the function is a function, but the inverse is not, so it's not one-to-one. It's only one-to-one if each of those or if both of those are functions, okay? The other way we can look at it is we can kind of do the same test we did before. I look at the original, and when I look at the original, I decide, okay, does every x have exactly one y? And when you look, you don't see any repeated x values. See, there's no repeated x values here, so I'm going to redraw that. But there is a repeated y value with the 3's, so it's not one-to-one. Essentially, that test that we use to determine if it's a function, we use that same test on the y values to take it a step further and determine if it's one-to-one. All right? So this one is not one-to-one for those two reasons. Okay? If I look at this one, again, I'm going to do the inverse here, so I'm going to find this inverse. I'm going to scoot that off to the side, give myself a little space. but I flip each of these ordered pairs, so I've got negative 3, 1, and then I've got 2, negative 1, and then it looks like 3, 0, and then 4, negative 4. Okay, so I write out each of these ordered pairs, and now I just want to determine if this thing is a, first of all, if f of x, if the original is a function. So I look for repeated x values. There are none. So this one is a function. Every x has exactly one y. I look at the inverse. The inverse is also a function because every x has exactly one y. And then the question is the function 1 to 1? And the answer is yes, it's 1 to 1 because the original was a function and the inverse is a function. Or you can kind of do that same test that we do for functions. I look for repeated x values. There are none. So that makes it a function. To take it a step further to determine 1 to 1, look for repeated y values. There are none, so it's also 1 to 1. Okay? If I look at something like this guy, when we're trying to find the inverse of sets of ordered pairs, that's pretty simple. We just switch each ordered pair and we reverse the x and the y. But typically when we're looking at functions, we're not looking at a straight out set of ordered pairs. We're looking at an equation like this. And even though this equation represents a set of ordered pairs, I couldn't write out all the ordered pairs and flip each of them. Okay? This equation is the equation of a line, and it has an infinite number of ordered pairs. So if I could write out all those ordered pairs, then I could switch each of them, and then I'd have the inverse, all right? But since I have this guy, let's think about what this really means. Keep in mind that this means y equals 2x minus 3. Remember, f of x is the same thing as y. So think about the basic concept of the inverse. I'm trading the places with x and y. I'm switching the x and the y values. They just trade places. And so before, when I looked at the ordered pairs, I was actually switching an actual value of x and an actual value of y. But now I don't have the values. I have x and y themselves, which should be just as good. All right. In fact, you might consider it to be better because it's going to give us all the ordered pairs that we're looking for. All right. So right here, I have an x and a y in here. Well, I'm just going to trade places. They're going to switch spots. So instead of y equals a 2x minus 3, I'm going to do x equals a 2y minus 3. Just like I did with the ordered pairs, I switched the places of x and y. Now I have an x and y, the actual variables, and I'm actually going to switch them. All right? But we would never leave an equation written this way. We always write equations in terms of y typically. So I'm going to rearrange this. I'm going to solve for y. So I'm going to add the 3 to each side. So I'm going to get x plus 3 equals 2y. Then I'm going to divide by the 2. So I'm going to get y equals an x plus 3 over 2. And that would be an acceptable answer. F to the negative 1 of x equals x plus 3 over 2. I could leave the answer that way, but there's actually a better way to write this one. If I divide by that 2, if I use my distributive property, it gives me this. It gives me a 1/2 x plus 3/2. And the reason that's a little bit better is because that's in slope-intercept form, y equals mx plus b. So there's a couple nice things about that. One, I'd be able to graph this thing. But two, I could even determine if this thing was 1 to 1 because I know that each of these is the equation of a line. I know that this guy, this first function, is the equation of a line that looks like this. And I know now that this second function is the equation of the line that looks like this. And I can use my vertical line test to determine that each of those are functions. So this is actually a 1 to 1 function, okay? So it gives us a couple little things like that. But really it is nice so that I can graph this thing. And the other thing that I want to point out here, if I look at the ordered pairs from each of these, like if I were to do just a quick XY chart from this original function, maybe I'll do like -2, -1, 0, 1, and 2. If I were to plug these values in, if I plug the -2 in, I get a -7. If I plug the -1 in, I get a -5. Here I get a -3, a -1, and a +1. That means that if I was looking at the inverse strictly from the sense of ordered pairs, the inverse to this function would have to look like this. I'd have to take each of these ordered pairs and switch them. It would be -7, -2, -5, -1, -3, 0, -1, 1, and 1, 2. And now think about this. If I were to take these values, these x values, and plug them in here, you can check them. If you plug the -7 in here for x, you're going to get a -2. If you plug that -5 in here for x, you're going to get a -1. If you plug the -3 in, you get a 0. If you plug the -1 in, you get a 1. If you plug the 1 in, you get a 2. And so what happens here is if I were to list every ordered pair from this original function, and then list every ordered pair from the inverse, I would see every ordered pair repeated, but the x and the y value switched, okay? So we're still following that same concept where we're switching the x and the y value. The only difference is that now I have every x and y value possible in the form of an equation, okay? So just keep that in mind. We're still applying this same concept, but we're just doing it algebraically and coming up with an equation of this thing, okay? If I look at the next one, again, I want to think about what this thing really is. This thing is really y equals x squared plus 2. So now if I want to find the inverse, I just rewrite it as x equals y squared plus 2. And I'm just going to solve this thing for y. I'm going to rearrange it, so I subtract the 2 from each side. Then with an x minus 2 equals y squared. And now I have to take the square root of each side. And that's going to give me y equals the square root of x minus 2. And most of us are going to write that as our answer. And that's not quite correct because we're overlooking a slight technicality. Remember, when we take the square root of each side, you have to have plus or minus that square root. And that's really important for this thing. And we'll see that when we start to graph these, is that if I don't have that plus or minus, I'm only going to have half of my graph, okay? Which means I'm going to be missing half of my ordered pairs, half of my function, half of my x and y values, and that's simply just not good enough, okay? So make sure you have that plus or minus to make sure that our inverse is complete, okay? And then kind of the same thing, but in reverse when we're looking at these things. So if I look at this guy, again, if I think about what this is y equals the square root of x minus 2. And so now what I'm going to do is I'm going to switch the x and the y value here. So I'm going to rewrite this as x equals the square root of y minus 2. And I'm going to solve this. To undo the square root, I'm going to square each side. That is an ugly looking 2. Let me try that again. And so what happens is over here I get an x squared. Over here the root and the exponent cancel each other out, so I get the y minus 2. And now I add the 2 to each side. And so what I find out that the inverse is y equals x squared plus 2, which can't technically be right, and it's not technically right. So if I put that up here, x squared plus 2, I'm going to put a little asterisk next to this because that's not quite correct the way it's written. And one of the reasons we can tell that it's not quite correct, when I look at the previous example, see the two values that I have up here are as inverses. Let me write these down a little bit lower. I have that a y equals x squared plus 2 and a y equals plus or minus square root of x minus 2 are inverses. And down here I have that an x squared plus 2 and a square root of x minus 2 are inverses. And so there's a little bit of a contradiction here. I know that this one up here is correct. I know that those are inverses. So in order for these to be inverses, we'd have to be talking about plus or minus. But since that was the original, I have to find a way to tweak the answer, the inverse, in order to make this thing true. And really the graph is the thing that's really going to help us out with this. And when we start to graph this, you're going to find out that what we're going to do is we're going to put a restriction on here that x has to be greater than or equal to 0. And really what that stems from is when we start to look at these graphs, this guy right here, that is a vertical parabola. This is a sideways parabola. Well, then this guy, because it doesn't have the plus or minus, is only half a sideways parabola. So when I find the inverse, I need only half of a vertical parabola, and that's what this does. It cuts half of it off. All right, and so the kind of reverse of what happened in the last example, I need the plus or minus to make sure that I have all my values. Well, here I had too many values, and I have to kind of cut it in half. And that's what graphing these things is going to help us do when we start to look at the graphs. Okay? But again, finding the inverse, pretty simple. We switch the x and the y, and then we rearrange it. We solve for y to make sure that this thing is in the proper format. Okay?